Fantastic. Hello, everybody. Hi, my name is Pavle Belanovic, and I'll be presenting with Jules. So in this talk, we'd like to tell you a little bit about how we use machine learning in Swisscom's mobile network, right? But in particular, like Elena's talk and also like in Daniel's talk, I'll focus on really the radio access network, right? Because the mobile network has different pieces, but I'll focus on the radio network. So like all the mobile networks in the world, also Swisscom's mobile network is developing over time. And actually here I'm just showing the last 4 years, and you can already tell just that the number of cells in the network has doubled. And that growth is not stopping. Yeah? So it's really quite a fast pace of growth. And you can also see that always new generations of technologies are coming in. So for the last couple of years, we also have 5G. One day there will be 6G and so on. So really what this means for us is that the complexity of a very important piece of work that we have to do, which is the optimization of the radio access network, is growing. First, it's growing because the number of units that we have to optimize is growing. We are at 100K and plus, and it's growing. But also because the number of parameters that have to be tuned is always bigger, right? 3G had some parameters, 4G has many more, 5G has even many more than that. So the number of parameters is also growing. And thirdly, and I think very importantly, the systems themselves are starting to have blurry boundaries. 3G was a completely separate system. You could tune it on its own. And then 4G came, and you could tune 4G, and that's it. But now with 5G, you start realizing that 4G and 5G have flexible boundaries that they can share power, they can share spectrum, and that in itself, in between the systems, is becoming a parameter to be tuned. So the complexity overall is really growing at a very rapid pace, and we basically predict that we will have 2.5 times more work in a couple of years from today than what we have today, and we are barely basically being able to optimize today. So the question becomes, how are we going to address, as a company, this fast growth in the amount of work that we have to do? And the answer is machine learning, right? That's where the machine learning comes in. It's a major component in our plan to address this growing complexity. There's other pieces of the puzzle, of course, that have to do with our processes, etc. But machine learning is a major component. And that's why we are preparing to launch a product called AutoTune, which is based on machine learning for this process. And that's where I hand it over to Jules to actually tell you how that works.
Thanks a lot, Pavle, for introducing AutoTune. So the idea of AutoTune is to automatically suggest parameter configurations for 4G cells. Now, to suggest parameters, to improve the performance of a cell, we need 2 types of data, at least 2 types of data. First, we need parameters, and we need performance data. We have 2 types of parameters. We've got physical parameters, like the height of a cell, and LTE parameters, like the emission power, for example. LTE parameters is really what we're focusing on here. These are the ones that we want to suggest for cells to improve their performance. And then finally, we have performance data that comes in the form of performance counters. And an example of that is the number of packets in the download. Now, all of this comes in via Kafka streams and is dumped to HDFS, from where we can process it with Spark on Kubernetes. Let's take a look at what we do with all of this data. First, we want to isolate occurrences where a LTE parameter change has a measurable impact on cell performance. To do this, we remove any data points that have physical parameter changes. And we also remove the days around these to ensure that the performance data that we keep is not influenced at all by any physical parameter changes. Now, on a side note, you may not realize this. Pavle has showed you we have over 60,000 4G cells in our network. But what he hasn't told you is that each of these cells has over 1,500 different configurable parameters. And each parameter, of course, takes multiple different values. Now, here, just a rough number. If each parameter only took 2 unique values, then we would have 10 to the power of 451 combinations per cell. Let's compare a bit. Do you know the number of atoms in the universe? Okay, well, it's 10 to the power of 82, roughly. So you see that we're not at all capable of tackling this task. It's very complex. And even if we were to hire everyone, all of the intelligent people here and all the people on Earth, we wouldn't be able to explore all possibilities. So back to our pipeline now. Fortunately for us, not all parameters are useful. We can actually disregard quite a few of them. And this will simplify our data set. By talking with experts, selecting LTE parameters that exist for most cells for a certain number of days in our data set, and that have more than 1 unique value, we can cut down the number of parameters that are of interest to us to around 300. Looking now at the rate at which this data is collected, we have parameters that are collected once per day, and performance counters that are collected once every 15 minutes. So we need to handle this data differently. To create our data set, we start by merging physical parameters with LTE parameters. This way, each data point corresponds to a change for a single cell at a given date with its current and its past configuration. Then we need to add the performance counters, but we can't do this quite yet. First, we need to use these counters to create indicators that Yelena talked about, and that give us actual insights into the performance of a cell, insights that we can understand. This is a crucial task that requires exchanges with experts from the domain to identify which performance indicators can be computed, which ones are important for us, and how important they are relative to one another as well. Initiating this discussion is crucial to ensure that you're doing the right thing and to start creating buy-in from your end users. And this is super important because if you don't create buy-in and talk with your stakeholders, then you can build something that works maybe really well on your own, but it's probably not the product that we want to build, and it's never going to be used. Now, before we can merge them, as any data set, we have missing entries. The data is not perfect. It's not an academic data set, so we need to deal with this. And we apply different strategies for the different data sets that we have. For parameters, we often use mode filling or forward and backward filling, whereas for performance indicators, it's often interpolation. As you probably know as well, we're dealing with time series data, and as I think Yelena and Joanna that I saw in this talk as well, we need to deal with seasonality when we're talking about time series data. So we looked at that, and actually, interestingly, first we removed it, but we found that it decreased the performance of the models, and we were actually introducing noise when removing the seasonality. So we put it back, and so we're handling it in a different way that I'll talk to you about afterwards. Now everything has been cleaned, so we can merge everything together. And after merging everything together, we augment our data set to include more date features and finer details about the performance indicators to capture the seasonality component that we didn't remove before. And this gives us our final features data set. But it's not the end yet. Now what do we have? We have a data set with performance data, current and past configuration data for cells, and performance data, past and future as well. So we're going to use this to build a model that can suggest parameters, and it's actually not just one model, it's 2 models that we need. The first one is a performance prediction algorithm, in which we input the parameters of the cells and past performance data, and this will predict the future performance of the cells. And we have this data so we can compare and we can evaluate. And with this performance prediction model, we create a performance aggregated score that we feed to a Bayesian optimization algorithm that suggests new hyperparameters that are then fed to the performance prediction algorithm in a loop. And of course, the Bayesian optimization remembers the parameters it suggested to suggest the best ones in the end. Now, if you followed, and I'm sure all of you know, there's really one thing that we need to focus on here. It's not this lovely part that will give us the best parameters that we want to use. It's the top part there, the performance prediction. Because if we don't have a good performance prediction algorithm, then we're just feeding garbage into the Bayesian optimization, so we get garbage out, right? Garbage in, garbage out. So we spend a lot of time and effort to try to optimize the performance prediction algorithm, to try to find the best one. And we explored many, many things. First, we tried multi-output ridge regressions, an MLP, and regressor chains ensemble. We found that the first two were the most accurate, so we disregarded regressor chains ensemble, we discarded it, and we tried LSTMs and transformers as well. Turns out that the task that we were giving to the LSTM was too complex. Our past performance data is close to 700 items long. One thing I forgot to mention is that we need to transform the pre-processing a bit for the LSTM and the transformer, because there we have to feed the whole sequence of past performance data to the models. And unfortunately, the LSTM wasn't performant enough for this task. After 50 items, its performance degraded severely. So we discarded the LSTM. And we're left with the multi-output ridge regression, the MLP, and the transformer. All three had similar accuracies, but for computational reasons and explainability reasons, we decided to discard the transformer. We actually decided to keep the multi-output ridge regression. But after a while, we found that it developed a consistent bias with the data that we had, and so we discarded it as well to use an MLP. Looking back at the project, I find it amazing, we find it amazing. The support that we can get when we talk with stakeholders, when we collaborate closely with them. But we also found that it was hard to get buy-in from stakeholders because we're using machine learning and they don't understand machine learning. And so it's difficult for them to trust the results that we're giving to them. So I'd say one thing that we want you to remember from this is that whenever possible, please keep things simple because it makes them easy to explain afterwards. This project also shows that that we can increase the rate at which we improve the mobile network many times over by using machine learning. And so that machine learning can bring real tangible benefits to mobile network operators and their customers. But this wouldn't have been possible either without the help of data engineers, data scientists, machine learning engineers, and managers across the whole company. We really need cross-domain collaboration to bring a machine learning model to production. And this is something that we've touched upon in the keynote sessions that you might have attended and other talks as well. We really need cross-domain collaboration to bring something to production. Finally, the process of bringing ML products to production requires a lot of undifferentiated work. And so managers should really strive to streamline this work to enable employees to focus on value creation. If there are only 4 things that you want to remember from this talk, please let it be them. Thank you for your attention, and we're open to any questions, of course.
Good. We start with a question from a colleague. It's Swisscom Mafia around. I have a question. You explained a lot. You explained very well how this works, but you didn't, unless I was asleep, you didn't speak so much about the actual results of the experiments. My understanding is that this is something that is running on production, like each day or every other day, whatever, you change the parameters to and measure the performance, and you have this feedback loop. But do you have concrete results on how much it improved, or how many people it replaced to work on that, stuff?
Yeah, sure.
Sure, let me just say a couple of words. This is very much a fresh product for us that, yes, has been developed with the domain experts, but this is not something that they are productively using today. So we're not there yet. However, we are right at the cusp of that beginning. So we have interesting data points, but it's still very early. I just wanted to say that.
We have prepared a slide on the results just to please you or anybody else that would have that question. Theoretical results, of course, where you see, okay, clear shift to the right? So on the left, the information that we have, and on the right, what we can optimize. There we go.
Yeah, thanks for your talk. I'm not an expert at all here, so I was just wondering, what are you optimizing for? So what are the results that you try to achieve? Maybe this graph tells me, but I'm
Not
sure.
really, no. This is the performance aggregated score, so it's something else entirely. Thank you for your question. We've actually got different metrics that we're optimizing for, and that's why we need, there we go, the performance aggregated score here. We've got 15 metrics that we're trying to optimize, and that have been classified by the domain experts into different categories with different weights. So you've got accessibility, for example, like if you can access a cell, and we have retainability, and the third one as well, and integrity. If the cell is functional.
Sorry, I'm jumping. It's the typical measurements of service quality that we use, expressed in terms of the PM counters that we have, right? So PM counters that tell us about the accessibility of the services, the retainability, so drop call rate and all the mobility-related counters, and then integrity, of course, so things like throughput. So it's all basically compressed and quantified in one.
And then if I anticipate your next question, maybe, this focuses on the cell level, but of course what's interesting for you is what you get when you're looking at your phone, right? When you're connected, how many times your video buffers when you're watching a video. If your call drops, or if it's handed over and you hear a click sound, things like this. And this is an area that we want to explore in the future. We have tools to get these measurements, but it's work to be done.
Do you think that so you said that you had to drop, for example, the transformer models. Mm-hmm. Do you think that the need of explainability and simplicity to explain to the stakeholders and everything, how much do you think this has an impact on the results? Like, do you think that giving a preference to simple models that still give good results, but how much better can you get even if you get, for example, a transformer, which is really hard, even impossible to explain? Like, how much can you quantify this difference, or even your opinion on it?
I think it depends on the people you're dealing with. It's always a question of people, right? Mm-hmm. They don't know ML, they don't trust ML, so whatever you can explain to them makes it better. And actually, at some point when we were evaluating the multi-output ridge regression, the MLP, and the transformer, we decided to go with so we discarded the transformer completely, but between the MLP and the multi-output ridge regression, we decided to go with the multi-output ridge regression, even though there was a slight degradation in performance, because it was just so much easier to explain to stakeholders. So I think it's better if you start with simple models to build trust with your stakeholders, and then you can move on to more difficult models. Yeah.
Thanks for the talk. So I saw you use past data to train the models. I was wondering if you also complement with some testbed experiments, maybe because some of the parameters or some set of parameters have not been tested in the wild because it never happened to come to that. Or how do you couple that with other tools to optimize, which do some optimization and stuff? So sort of two questions. So how do you cover cases that you may have not seen? And how do you couple that with traditional optimization? So because maybe AI is not always the best answer to a given problem.
Yeah, you're right. So for parameters that we haven't seen, this is something that we'll have to see when we go to production. Not the best answer, I know, but it's just the way it is. We can anticipate by looking at some parameters that vary very often. And we know the range of values that they can take, and so we can simulate these and go to the tuners and ask them, well, do you think this is reasonable? And if it's not, then we look back. If you have any suggestion on how to do this properly, yeah. No, it's just, yeah. Mhm.
So to simulate exactly this case which I have not seen. And then perhaps there are tools that are used today for optimization, which is not ML driven. So how will you tackle that? That's a different question.
Yeah, so for that second question on coupling tools that exist and that aren't ML driven with this, it's very much an area that we're exploring right now, that we're talking about. Yeah, that would be great.
I mean, it's basically a little bit the topic of the plan that I mentioned at the beginning. This is really a very big area of work for Swisscom that, I'd need another quarter of an hour or so to talk about the entire plan. It has a lot to do with processes and a lot to do with existing tools, as you say, as well as introducing more than one new tool based on machine learning. This is one. There's others, actually. So we're carefully evaluating which parts of the parameter space are going to be handled where and what is going to be done by humans, right? Because that's the limited resource. And actually, just to give you an idea of what that looks like, we're forming a pipeline of work that will be done really by people, and this is where this comes in as recommendations. Work that is semi-automated, that is really human supervised, done by tools that really create configurations themselves, and then full automation, which is really all the part of the work that you can actually fully trust to be completely under the hood. So yeah, it's a bigger picture where this forms the part on that left part, of the picture.
Maybe the last question. I've seen several research on the optimization of parameter with reinforcement learning models. Did you test that also? Something like Bondy-Monchou, I don't know what is the name in English, sorry.
Currently not, no. We're using tree parson estimators for the optimization.
Okay, so I think we went a bit over time, and the break was again planned to be 5 minutes, so I don't think it's worth taking an actual break. Sorry about that. Thanks again for your presentation. So